Okay, so now we're going to discuss nucleophilic, aromatic substitution, or SNAr, and how this differs from electrophilic aromatic substitution, which was the previous video. Okay, so in this case, benzene, or the aromatic ring, okay, is going to be our electrophile, E+. Okay, so it's not acting as a nucleophile now, it's going to actually act as the electron deficient source, or the electrophile. And we're going to have to attack it with some kind of nucleophile. Okay, and the point is to substitute the ring with that nucleophile. So you should know, before we jump in, I'm going to do an example, but you should know that you need a leaving group for this and an electron withdrawing group. Why would you need an electron withdrawing group? To withdraw electron density out of the ring and make it a better electrophile. Okay, so the more electron deficient the ring is, the better it will act as an electrophile. Okay, so the more attackable it will be, basically, if that makes sense. So let's just jump right into an example. And remember, when we do nucleophilic aromatic substitution, or SNAr, we really need to know our resonance, and you'll see right now. So I'm going to start with this structure here. Our leaving group is going to be Cl in this case. You can have basically any halogen be your leaving group, even fluorine in this case. Okay, so we have NO2, and we're going to have to draw this structure out. Then we have another NO2. So like I said before, you better know what it looks like, or else you can't do these resonance structures, right? We're also going to need a nucleophile. This is our overall reaction, so we'll do the mechanism in just a moment. Okay, so nitrogen can act as a nucleophile here. It just has a CH3 attached, which I'll be drawing that methyl group as a line bond in a little bit, so you'll see what I mean. This is our nuke though, good to know. And we also need some heat, that's what the little triangle stands for. And we will end up with, so the product that we're going for is our benzene ring, substituted with our nucleophile. Okay, notice how it's lost an H, so that's something we're going to have to take care of. And then there's our methyl group, which is this. Okay, and that's the new bond that we formed. We also have our NO2s, which didn't leave, but they're essential in this mechanism. So we're going to have to know how to use them. Okay, so let's start. So for the mechanism, I'll just put it below. I'll kind of use this as part of it for the structure, so I don't have to keep redrawing. Honestly, the most tedious part of this mechanism is continuing to redraw the resonance structures in every frame, but you need to make sure you account for every detail, or else you're going to lose really easy freebie points. So don't let that be you. I know you guys got this. So the first thing we're going to do, so step one is, so before we even start, which carbon on our starting material here is the most electrophilic position? Can we tell? So go ahead and look at that, try to decipher, right? And it's going to be this carbon here. It's going to be pretty partially positive because of this induction effect from our halogen leaving group, right? The leaving group is not going to leave automatically though, as you'll notice in the next step when I draw it in, because this is not SN2, right? Or else we wouldn't even need all of the resonance structures that we're about to draw. But that's not the case with benzene, so I'm showing you what we're doing. It's SNAr, right? So the first step is that we're going to have our nucleophile attack right there at that carbon, and then these double bond electrons are going to be donated to that carbon right there, okay, where our first electron withdrawing group is. So this step, so step one is the nuke, or the nucleophile attacks partially positive carbon, right, on the ring, and moves double bond electrons to the adjacent carbon. Okay, and this step is called addition, right, because we're adding our nucleophile. Okay, so the addition of the nucleophile right there. Okay, so in the next frame, here's what we have. So it's gonna look a little wacky, but I'm gonna walk you through it. So our leaving group hasn't left yet, okay? Our leaving group has not left yet, so there it is. We also have our nucleophile that we just added. I'm gonna draw it in red. So we have our nitrogen, right? It has 2 H's still, and our methyl group so far, okay? But since it has 4 bonds, it's gonna be what, everyone? Yes, very good. It's gonna be positively charged. Okay, so make sure you account for all your charges as we've been doing. Okay, and we also have, connected to the ring, our 2 NO2 groups, nitro groups, right? So here they are. You're gonna need to know what they look like. You're gonna have to know this structure. I'm warning you from now. Okay, and our other one that's attached right here. Okay, make sure you account for all your charges. What else is missing from this is our lone pair, right, that we put on this carbon. So it's going to make it negatively charged. So we have electrons right there. And we're going to have to make some resonance structures now. So these resonance structures basically like demonstrate how this minus charge is delocalized around the ring and through the 2 nitro groups as well. So that's why we need our nitro groups for resonance, for stability, right? And stability in chemistry is the magic word. We're always trying to get to a more stable state for our molecules, okay? So we're going to put these electrons into we're gonna donate them and resonate them around the ring, but we have to involve our electron withdrawing groups. So right here, we're gonna make a double bond, and these electrons will be pushed up to this oxygen. So that's our first resonance structure, so we're going to need resonance arrows, okay? It's different than a normal arrow, as you can tell. So I'll say step 2 is move lone pair electrons into first EWG, right? So we need resonance for that. So this is our first resonance. We're starting our resonance, right? And so basically now, as you can kind of predict, for the rest of this mechanism, we're going to be moving this charge around the ring and kicking off our leaving group. So that's our goal right now. So with that goal in mind, you can kind of predict what I'm going to draw, but I'll still draw them. So, oops. So yeah, there shouldn't be a bond there. It's going to be right here. We still have this nitro group. And up here, what we have so far is this double bond here, right there, and 2 of these, right? And this is still positively charged. Good, so now we're gonna actually do 4 arrows to move this charge down to our second electron withdrawing group, excuse me. So we're gonna have these electrons, right? They're gonna move down. And then these electrons are gonna move here. Okay. And then these electrons are going to move here. And then we're gonna have these electrons move out here. Okay. And we still have our leaving group and our protonated nucleophile attached to the ring, right? It's a mess, I know, but it's not too difficult once you know what you're doing. Okay, so in this case we have move minus charge to second electron withdrawing group and more resonance, right? So we need another resonance structure. So don't forget your resonance arrow. And our next resonance structure is going to look like this. So we still have our ring. Let me make sure to draw these alkenes in correctly. So right now we have this here. We have these 2 bonds in benzene. We've got this down here at our second electron withdrawing group that's involved, right? This one's now back to normal up here. Okay. We also still have our leaving group we haven't made it leave yet, and our protonated nucleophile. Again, guys, bear with me. It's literally the drawing in this case that takes forever, but I hope you see that it's pretty simple and we're just resonating around the ring. So the next set of arrows is going to be basically moving this one out of the the second electron withdrawing group. So we'll take these electrons, we'll move them in here. These electrons will go there, and then we'll move these electrons up to this adjacent carbon. So more resonance, basically is step 4. Okay. And now, so we need another resonance arrow. Okay. And in this structure, we're going to be left with this. Okay, so we're starting to move these alkenes, right? And we have a minus charge here. This nitro group is also back to normal. Okay, and we have another nitro group, of course. Just trying to make sure I don't miss any little detail. And then we still have, so it's about to leave now. We've got our Cl leaving group. And we have the nucleophile that we added way back when, still protonated, right? So the next thing that's going to happen is these electrons are going to donate to this, to form this double bond here. So these electrons will donate into here. But of course you can't have 5 bonds to carbon, right? No Texas carbons. Dr. Ko hates that. So goodbye leaving group. Okay, so step 5, pretty crucial, right? So now we're going to donate lone pair electrons to basically reform the pi system, right? Because they're going to donate here and we're going to have 3 double bonds again in benzene and subsequently kick off the leaving group. Okay, so this is elimination, right? We're eliminating the leaving group. Okay, so we're going to be left with now we have our double bonds like so. We have our NO2s, right? We're not going to be using them anymore, so that's why I drew them like this. And now, so our Cl is gone, so let me draw that out here. Okay, remember it's got lone pairs to use. It's negatively charged when it's on its own. And we also have our protonated nucleophile, which is still positively charged because 4 bonds to nitrogen, right? And so we're going to need a base to come in and deprotonate that for us. And the best thing to use, I guess, is Cl because we have it, right, in solution. So you can go ahead and get rid of that extra H. And finally, we're gonna, we'll just get this product, right? So this is our final product. So we have successfully substituted the nucleophile on our electrophile ring. Okay, and that's the difference between nucleophilic aromatic substitution, or SNAr, and SNAr, which was in the previous video. I hope that was helpful, and let us know if you have any questions.